Picture this. You're cruising down the highway at 70 miles per hour. Or maybe you've just left your brand new EV parked in the garage for a week only to come back and find the battery completely dead. Why? Well, it's because the car's heartbeat monitor, the battery management system, is detecting these chaotic, massive currents that literally do not exist. It's hallucinating. And in the world of high-voltage power batteries, a hallucinating sensor isn't just a minor glitch, it's a critical safety hazard. Welcome to today's explainer. I am super excited to take you on a deep dive into the absolute fail-safes of an EV's battery management system. Specifically, we're focusing on current sensor protocols. This is the frontline defense against catastrophic electrical failures. We're going to explore exactly how engineers predict, diagnose, and ultimately neutralize these threats before you even realize anything went wrong. Okay, let's look at our roadmap for today. We're going to move from chaotic real-world threats all the way to meticulous validation. We'll hit fault root cause analysis, architecture and fail-safes, DFMEA design measures, PFMEA process control, and finally wrap up with DVPR mass production validation. All right, kicking things off with Section 1, fault root cause analysis. We need to figure out what's going wrong. You can really think of these sensor faults as the EV's cardiac arrhythmias. The current sensor gives us the most critical metrics for the car: state of charge, battery health, overcurrent prevention. So when it starts sending garbage data, we have to diagnose it instantly. We basically categorize this electrical chaos into 3 distinct diagnostic codes. First up, P0AC1. This is when the signal drops dangerously low, under 0.5 volts. Usually, this means a disconnected pin or a wire rubbed against the chassis and shorted to ground. Then we have P0AC2, where the signal spikes way too high, above 4.5 volts. This is almost always water ingress or moisture causing a micro short straight to the power supply. And finally, the weird one, P0AC0. This is just an completely unreasonable value, often caused by thermal drift or something even stranger. And that stranger thing, that's magnetic saturation. Imagine a massive transient current shock, like a huge surge during startup or a brief external short circuit. This blast of energy rushes through the Hall Effect sensor's magnetic core and actually leaves behind residual magnetism. It physically shifts the sensor's baseline voltage away from its perfect 2.5 volt center. The result is the creation of that dreaded ghost current we talked about. Because the baseline shifted, the BMS thinks there's a continuous current flowing. So, while your car is parked, totally asleep, this ghost current tricks the system into mathematically draining your battery's state of charge calculation. Crazy, right? So how do we shield against this? That brings us to Section 2, architecture and fail-safe. We obviously can't let ghost currents or short circuits ruin the vehicle. To achieve the insane safety levels required in modern EVs, engineers rely on true heterogeneous redundancy. Meaning, they don't just throw 2 of the same sensors at the problem. They use 2 completely different technologies working together. On one hand, you've got the shunt resistor. It's slow, but it has micro-ohm precision, making it perfect for tracking low, steady currents flawlessly. On the other hand, you have the Hall sensor. This thing delivers the lightning-fast response times needed for extreme, high-current situations. If one technology develops a blind spot, the other is right there to back it up. But here's the catch. Having 2 different sensors is totally useless if their data isn't perfectly aligned in time. Enter the hardware synchronous latch. The main MCU actually has dual independent analog-to-digital converters, and it forces them to capture these redundant signals in the exact same microsecond window. You might be wondering, does a microsecond really matter? Absolutely. At high speeds, even a millisecond gap means missing huge chunks of energy data. By locking these readings together, the system completely eliminates the calculation drift that would happen if the timestamps were even slightly off. Now, what if a catastrophic fault strikes while you are actively driving down the highway? Say the sensors just go completely blind. Does the car just violently shut down? No way. The Level 4 life support system instantly kicks in and restricts available power by over 60%. The vehicle immediately drops its complex current counting and defaults to a very conservative pure voltage boundary protection mode. The warning lights come on and it safely limps the car off the highway. It keeps you, the driver, in control, instead of executing a terrifying shutdown at high speeds. All right, moving into Section 3, DFMEA, Design Preventive Measures. Obviously, we want to avoid limp mode entirely if we can, which means proactively fighting these risks through intelligent software. This is such a cool example of software literally healing a physical hardware issue. Remember that residual magnetism causing those ghost currents? engineers built a smart, zero-offset calibration algorithm to fight it. While the vehicle's asleep, the high-voltage relays are physically disconnected, right? So true current is absolutely guaranteed to be zero. At that moment, the software quietly wakes up, reads the sensor's current voltage drift, saves it in memory, and then mathematically deducts it on the very next startup. The system is actively healing itself by erasing the magnetism while you sleep. Which leads us to the factory floor. Section 4. PFMEA, Process Control Methods. Because, let's be real, a brilliant software design is only as good as the physical hardware it runs on. This is where the meticulous blacksmiths of engineering step in to ensure mass production realities don't ruin perfect designs. Just walk through the assembly line with me for a second. First, automated servo tools tighten bolts with 100% smart torque controls so mechanical stress doesn't warp the metal. Second, operators literally listen for a physical click. That's the double lock safety mechanisms engaging, ensuring pins never vibrate loose on a bumpy road. Third, an automated end-of-line testing system forces a multi-temperature calibration. And lastly, they apply a vacuum conformal coating to the circuit boards to completely block out moisture and prevent microshorts. It's incredibly thorough. Finally, Section 5, DVPR Mass Production Validation. So the software is written, the hardware is built, now we enter the engineering torture chamber to guarantee fail-safe operation. Take a look at this extreme transient pulse test. Bar 1 is our normal state, resting totally safe at 0 amps. Then, out of nowhere, bar 2 hits, a vicious 900 amp short-circuit strike lasting 100 milliseconds. It is a massive surge, designed specifically to permanently magnetize the core. But check out bar 3. In less than 500 milliseconds, the active software catches the anomaly, executes that smart 0-point calibration, and rapidly snaps the baseline back to a perfectly safe 2.5 volts. It intercepts the ghost current threat almost instantly. And then we throw it in the oven, literally. For the intense Joule heating test, we bake the shunt assembly in an 85 degrees Celsius chamber, while simultaneously blasting it with a continuous 400 amp discharge. The metal is basically roasting. But to pass, the thermal coefficient of resistance must stay below 25 parts per million, and the current gain error has to maintain a razor-thin sub-0.5% accuracy. The hardware simply has to refuse to drift, even under compounding extreme heat. Let's look at the exact timeline of a worst-case scenario. A totally severed sensor wire. Boom. At exactly 0 milliseconds, the fault is injected, the wire is cut. By just 100 milliseconds, the system debounces the signal, verifying it's a real fault and not a split-second glitch, and accurately triggers the P0AC1 or 2 fault code. And by the strict 2.0 second functional safety limit, the vehicle reacts. It drops into that pure voltage mode and securely reduces powertrain output by over 50%. In literally the blink of an eye, the car intercepts a catastrophic failure, shifts its software strategy, and keeps the driver safe. Which brings us to a bit of a provocative engineering cliffhanger. We've just seen how incredibly robust these current sensor fail-safes are, but what if we zoom out? Should voltage and current fail-safe modes strategically overlap? I mean, if our current sensors go blind and fall back to a voltage-only mode, what happens if a single-cell voltage wire snaps at that exact same time? How do you map out the timing for those overlapping degraded states without instantly shutting down the car on the highway? That right there is the bleeding edge of functional safety. The next layer of defense engineers are actively solving today. It's a fascinating challenge to think about. Thank you so much for joining me on this explainer. I hope it gave you a fantastic look into the hidden safety architecture of modern EVs.